Hi, I'm Dr. Johnson Haas, and welcome to Earth Parts. So I keep talking about accretion of a star and planets out of this initial cloud of gas and dust, but what is actually accreting during accretion? As I said, it's mostly hydrogen and helium. The solar system is overall what we call solar in composition. It's about three-quarters hydrogen, about a quarter helium, and only about 2% heavier elements heavier than helium on the periodic table. Mostly it is light gases, hydrogen and helium. And that's what the sun is made out of. The sun is 99.9% of the mass in the solar system. To a first approximation, the sun is the solar system. The planets are tiny by comparison. But they are made up of that 2%, largely. Hydrogen and helium are the primary constituents of Jupiter and Saturn, the gas giant planets, but the rest of them are made of the heavier elements, and it's only a tiny fraction of the sun that's comprised of this stuff. The planets you can think of are almost like the dregs left over from the formation of the sun. So what kind of processes are actually going on during accretion to have it happen? And the first thing you think of is gravity pulling it all together. And of course, gravity does pull the whole cloud together to form a propylid that forms a protoplanetary disk that will form star and planets, or multiple stars and planets. But that's not where it starts. Where it starts is on a much finer scale of individual atoms interacting. And these things condense. They essentially are condensing as water vapor would condense. As you change the temperature in a room, the water vapor in the air would condense to a liquid. And that's essentially what we're talking about here. As it's coming in closer to the star and being compacted more, the gas reaches a density to where it has to condense out to form solid or liquid objects, droplets of molten metal or molten silicate rock, little bits of dust. And once you have these tiny, tiny particles, they can begin to associate with each other. They can begin to flocculate. And we think what happens is, at this point, the small particles are being bathed by ultraviolet light from the young sun, and this will tend to impart a static charge to the particles. The photons that hit the particles can knock electrons out, can ionize some of the atoms in that particle and impart to the surface of the particle an overall static charge. And like feathers sticking to a balloon with static charge, you can have these particles begin to clump together to form little loose associations of lots and lots of particles clumping, flocculating together. And this can be either particles of rock or particles of ice, or obviously if you have little droplets of molten material, then they'll not just flocculate, they'll actually merge to form larger droplets. So that gets you started. And then you also have direct vapor deposition of the gas that's still there, the stuff that, the gas that can condense, the gases of light volatile compounds like CO2, water, methane, ammonia. Those things can deposit directly onto the surfaces of particles once particles are there. So once these particle clumps have accumulated, the clumps will begin to flocculate with other clumps. Once you get to a certain size of grains and particles clumping together, you form little sand and boulder-sized objects out of clumps of smaller objects, and they consolidate into larger and larger things. Once you get beyond the boulder size, then at that point, gravity starts to take over as a more important process. And here you can see in this NASA animation, direct vapor deposition. The vapor is depositing on these little particles that are already there, and it makes them bigger. Obviously, it's growing them. But if they bump into each other while this is happening, it's going to stick them to each other. They're going to adhere, and you start building bigger and bigger rubble piles of material. So let's talk briefly, before we go on, about the growing of planets. I want to talk more about what those heavy elements really are and what the rest of the condensing stuff is like. The hydrogen and the helium don't condense. They remain as a gas. They don't form condensed solids during the accretion process. That's just not how those elements behave. What you're looking at here is a chart showing along the x-axis the Z number or atomic number of elements on the periodic table. Hydrogen has a Z number of 1. It's the lightest element. Uranium, as you see here, is the heaviest naturally occurring element at a Z number of 92. Hydrogen and helium are by far the most abundant elements in the universe. The hydrogen and helium that makes up the sun is mostly primordial. That is, it formed as a result of the Big Bang, the initiation of our universe about 13.8 billion years ago. But it's the most abundant stuff out there. The rest of the periodic table is the result of prior generations of stars contributing their remains to the molecular gas cloud that would have formed our sun. Earlier generations of stars seed this interstellar material with heavier elements that are produced in stars by fusion reactions. All the elements in the periodic table heavier than helium are produced in stars by nuclear fusion reaction processes. The interesting thing is that next in abundance after hydrogen and helium, the most abundant elements in the sun, outside of those two lightest elements, are carbon, nitrogen, and oxygen. And this is interesting because these elements are necessary, for one thing, to make organic compounds, to make life. And it's interesting that some of the most common elements in the solar system, in the universe at large, are in fact the elements that you need to form organic compounds and life. These also form what we call light volatile gases and ices. You'll form out of carbon methane, or CO2, or carbon monoxide, and all these can freeze out to form solids in the outer part of the solar system when it formed. Next, in abundance after carbon, nitrogen, and oxygen, the life-forming elements, if you want to call them that, the light volatile, icy, ice-forming elements. Next after those are the rock-forming elements. Silicon combining with oxygen, aluminum, calcium, sodium, potassium, sulfur. These are where we get most of our rock-forming material. Silicate rock makes up the mantle and the crust of our planet. And most meteorites are stony, meaning they're made of rock. These are very abundant elements, and the terrestrial planets are primarily made of them. And then you have iron here, too. Iron is very abundant. And not only does it form our core, which is nickel-iron alloy, essentially, not only does it form our core, but it's abundant enough that it's actually a major rock-forming element, too. Iron is abundantly found in silicates, complex silicates making up the mantle and the crust of our planet. If you go further down the periodic table, on the diagram here you see the abundances fall off dramatically. If you go to heavy elements, you go all the way down to look at things like platinum, lead, thorium, gold. These are the lowest abundance elements in the solar system. They make only a very tiny amount of what the planets are made of. And so we look at these things often as rare ore deposit minerals because, in fact, they are rare. Their abundances are quite low. These are the heaviest elements that stars can produce during fusion reactions. And they don't produce much of it. And most of that was produced during a supernova explosion. During supernovas, you can fuse the very heaviest elements in the periodic table. In the last moments of a star's life, intense, highly energetic reactions occur as a star detonates that can slam together nuclear particles and make fairly large nuclei. Now, to make objects larger than small clumps and rubble piles, gravity is obviously necessary. This is what drives the process at that point. Tiny particles don't gravitationally attract to each other, not that well in comparison to large objects. And so the flocculation processes and direct vapor deposition, condensation processes led to planetesimal bits that were small, that would associate into rubble piles that got bigger and bigger. And at the point where you're the size of a mountain, gravity begins to cause everything around you to start moving toward you. Objects are attracted to the largest local center of mass. So, as these rubble piles begin to grow, they grow into larger and more massive objects. The most successful, if you want to call it that, of these objects begin to dominate their orbital pathway and become the primary attractors of the remaining unbound material. Once an object gets to be larger than a few kilometers in diameter, the process goes pretty fast. It begins to sweep up material pretty readily in its surrounding orbital region from the star, and grow within a period of just a few dozen million years into a fully sized planet. The following is a computer simulation from a study from 2010 showing how an accretion disk actually organizes itself into protoplanets and then finally into planets. In this simulation, you're looking down the poles, straight down onto an accretion disk. And the authors have color-coded it by density. So the highly dense hot material is close to the star, and then it fades away as you go further out. So they're starting with a pretty homogeneous disk here of material. And what the simulation does is to give each little finite element in that particle cloud its own mass, velocity, momentum, and of course gravity. And of course the sun in the center has gravity. So as the simulation plays out, it's very much a calculation of fluid dynamics within a rotating disk with gravity added in, creating attractors that then grow as they get fed with surrounding material. So let's watch it play out. So what you're looking at here, at this point in the simulation, a number of protoplanetary nuclei have formed. At the very beginning stages of the simulation, even as it started to run, you saw that what was initially homogeneous disk organized into streamers of material, looked very much like a spiral galaxy actually at one point early on there. And now you have distinct planets, but notice that these planetary cores that are developing, these planet nuclei, are not in particularly stable orbits. They're in elliptical orbits, they're interacting with each other, they're losing mass to the star if they get too close. And at this point, in real life, they would be incandescent hot, constantly impacting smaller objects. A very chaotic scene. So let's continue. And here we are sort of near the end of the simulation, and you can see how it's played out. At this point, there are a few planets that remain. Most of the ones you saw beginning to form were destroyed by falling into the sun. Maybe they were slung out of the system entirely. Only a few are going to end up having stable orbits that will remain over geologic time. And it's very likely that in our own solar system, as it formed, there was a lot of violence like this going on, and we may have even had several planets that formed that we lost. We don't know, and it's really hard to tell now. Hi, I'm Dr. Johnson Haas, and welcome to Earth Parts. So I keep talking about accretion of a star and planets out of this initial cloud of gas and dust, but what is actually accreting during accretion? As I said, it's mostly hydrogen and helium. The solar system is overall what we call solar in composition, a propylid that forms a protoplanetary disk that will form star and planets, or multiple stars and planets. But that's not where it starts. Where it starts is on a much finer scale of individual atoms interacting. And these things condense. They essentially are condensing as water vaporized of this stuff. The planets you can think of are almost like the dregs left over from the formation of the sun. So what kind of processes are actually going on during accretion to have it happen? And the first thing you think of is gravity pulling it all together. And of course, gravity does pull the whole cloud together to form approximation. The sun is the solar system. The planets are tiny by comparison. But they are made up of that 2%, largely. Hydrogen and helium are the primary constituents of Jupiter and Saturn, the gas giant planets. But the rest of them are made of the heavier elements. And it's only a tiny fraction of the sun that's comprised. It's about 3/4 hydrogen, about 1/4 helium, and only about 2% heavier elements. Elements heavier than helium on the periodic table. Mostly it is light gases, hydrogen and helium. And that's what the sun is made out of. The sun is 99.9% of the mass in the solar system. To a first